Okay, so we're just going to start, as we've done before in the past, we're just going to start with a review, and the review will establish continuity to the new material that will be presented today. So the first thing I want to do is talk about a little review of classical psychometrics, and I found this slide and I thought it was kind of interesting. And essentially what I want to say is that classical psychometrics is a little like Russian dolls. So as you can see here, you have a picture of Russian dolls. The thing that defines the Russian doll is that you can untwist the head off of the Russian doll and you open it up and there's another little doll inside it. And you unscrew the head off that one and you open it up and there's another little Russian doll inside it. And you take that one out and you unscrew the head from that one and you open it up and there's another little Russian doll inside it. And that idea pretty much, I guess, continues forever. But that's a little bit like classical psychometrics in that in classical psychometrics, we have the idea that big dimensions contain little dimensions. Now, with the Russian doll, of course, each Russian doll only contains one Russian doll inside it, which contains another Russian doll, which contains another Russian doll. But in psychometrics, ideally, each big dimension could contain 2, 3, 4, 5 different subdimensions. And that's what the essence of content validity is. It's just finding out what the parts are inside each thing. So let's compare classical test theory to the Roche analysis. In classical test theory, it is the corrected item total correlation that pretty much sums up the relationship between the item and the scale. Okay, everything that relates to the item and the scale is pretty much summed up in the corrected item total correlation. All right? And because it's simply a correlation, we really don't know, for example, where the lowest level of the item begins and where the highest level of the item stops. We simply know that the item and the scale covary. Okay? We know that the item spans part of the trait, but we don't know how much of the trait the item actually spans. And that's different than the Roche idea. Because in the Roche idea, in addition to having a point measure correlation, which, as you recall, the item polarity table gives us, each item now gets a difficulty parameter that's associated with it. And the idea of the difficulty parameter is that the difficulty parameter spreads the items along a latent dimension, okay, a latent dimension of ability or a latent dimension of the amount of the trait. And this leads to a question. Does the fact that these item difficulties are dispersed, does this map on into anything in the real world? Because now we actually have the ability to locate the different levels of the item along the span of the latent trait. And if we take the average of those levels of ability of the item, then that's what's called the difficulty of the item. So it's actually not just one logistic curve per item. It's actually a logistic curve for every level of the item, okay? So if we have these multiple difficulty levels dispersed over the entire range of the latent trait or the latent ability, does that map on anything in the real world? And the answer is that, in fact, yes, it does. That's supposed to map onto something which is called the item hierarchy. And the item hierarchy, in fact, is supposed to be dictated by the theory. So the fact that the items are now distributed along the latent continuum, this is supposed to converge closely with the theory, and this is supposed to, in fact, validate the theory. Okay? And this is a different idea of construct validity. All right, so when we talked about construct validity in a classical sense, in a classical test theory sense, we're usually talking about an extrinsic model of validity. So the idea is that you will select items, and you will invent the scale, and then you're going to study the correlation of the scale with many, many other scales. And you hope that those correlations are roughly in accord with what you would expect in terms of the magnitude and their direction. So, for example, virtue scales should be inversely correlated to personality pathology scales, hopefully substantially inversely correlated. And that's about as precise as it gets, unfortunately. So the idea here with construct validity in a Roche framework, it's an intrinsic notion of validity. We don't have to leave our items in order to actually validate the scale. What we're trying to do is to validate the item hierarchy or the item order. So you may have some ideas about religiosity. Maybe you have some ideas about how religiosity eventually saturates identity. The only thing that is available to you is a population of college students. So you begin your scale construction process with college students. And with the college students, you're able to work out this ruler here that varies from 0 to 9, let's say, just an arbitrary scale of measurement. But your theory doesn't really get interesting until you get people that are professionally involved in religion in some way, religious institutions. But your ruler doesn't go up that far yet because you don't have anybody in your sample that represents these people yet. So the idea here with the Roche model is that all of the intervals are equal. The distance between 2 and 3 is equal to the distance between 7 or 8. And up here between, say, 7, 8, and 9, these are going to be my most difficult items for the college students. However, what I can do, I can get additional people that are not college students that are involved in religious institutions, and I can study the relationship between identity and spirituality or religion that way. I can actually extend my ruler. Okay? The Roche model gives us a way of doing that. So the Roche model tells us the item hierarchy. Well, the theory tells us the item hierarchy. The Roche analysis tests the item hierarchy and gives us a way of validating the items at the upper end of the item hierarchy. And as I said, these two notions of construct validity, they're two very different notions of construct validity. The Roche notion of construct validity is actually intrinsically more efficient. So given that, how do we calculate the difficulty levels of the items? Now you remember that Roche asked what happens when a person meets an item. And the idea here is that when a person meets an item, there's a tug of war going on. And we don't know who's going to win. You can think of it as a tug of war, you can think of it as a wrestling match, you can think of it as a chess match, but the relationship between person and item is not deterministic, it's probabilistic. So if you're facing an opponent like Garry Kasparov in a chess match, well, he's going to defeat you every time. And we're not going to learn much about what your ability is. We're going to learn something about your ability when the difficulty levels of the items begin to match your ability, when they begin to come close to your ability. And at the point at which item difficulty matches person ability, the chance of success on the item is going to be 50%. So if we give a bunch of items, we take time to look at our theory and we ask ourselves what items issue from our theory, and we administer those to many subjects. And if we arrange our persons and items in a particular way, we can get something called a scalegram that has 3 zones in the data. So the scalegram has the high ability subjects at the top, the low ability subjects at the bottom, the easy items on the left, the hard items on the right. And then the scalegram is divided up into 3 zones. So up here in the upper left, we have a situation in which the high ability persons are taking the easy items. We expect this in this region, all items will be passed. Over here we have a situation in which low ability subjects are taking hard items. We expect all items will be failed. And then in the center we have this transition zone. So if we take the scalegram and we add a couple of columns to it, we can actually bridge our way from qualitative data to genuine interval level data. So we add an item over here that represents the proportion of items passed. The proportion is going to be an intermediate step into getting us to interval level data. Okay? And even if we have missing data, we can still construct a proportion. So missing data doesn't necessarily hurt us. So over here we have proportions in this column, this rightmost column. And then in this bottommost row we have proportions. And what we do, we take the natural log of the proportion, and that expands the proportion, which only varies from 0 and 1, 0 to 1. That expands the proportion from essentially minus infinity to positive infinity. And that's how we get from qualitative data to interval level qualitative or quantitative data. So here we have our scalegram, and here we have our transformation of the qualitative data into proportions and then interval level data. And you can take these numbers, which will be juggled by win steps in order to minimize the amount of mispredictions in the matrix. Basically, these numbers can be transformed over into the person item map. And now we have the persons and the items in the same frame of reference. So we just made it from qualitative data to interval level data, which is actually pretty cool. Now when we look at the structure of the WinSteps file, WinSteps is our great program for doing ROS analysis, right? We find that there are 3 regions in it. The topmost region has the commands, the central region has the items, and everything after a semicolon is a comment in WinSteps, and the bottommost region actually contains the data, which is going to be the item level data along with the person variables. Okay? And there are 2 ways to do item selection in WinSteps. So the first way to do item selection is to use the IDelete statement. And any item number, it's going to be item number space, item number space, item number. Any item after the IDelete statement will automatically be excluded from the analysis. The second way is to use the iSelect statement. So if we have iSelect in this example, iSelect equals FFM, that's going to select any item that starts with the letters FFM into the analysis. Anything that doesn't start with the letters FFM will not match this character string and will be excluded from the analysis. So all you would have to do, if you can see this slide, all you would have to do would be to uncomment one of these lines, and you can very quickly switch what scales you're analyzing with WinSteps that way. Now the first thing that you're going to look at when you begin to analyze these scales is the item polarity table. And the item polarity table contains the entry column over here on the left. This basically gives you the item number. And we'll just go over a few of the more important columns here. Then the measure column, this is the difficulty levels of the item. And then the infit and outfit columns. And you're going to notice there are 2 parts here, MNSQ and ZSTD. This is the Z-score of the fit of the item. This is going to be heavily influenced by sample size. The mean squares, this puts all of the fit statistics on the same metric. So this is the one that you're usually going to be looking at. Values greater than 1.4 or less than 0.7, or some people say 0.6, are going to be suspicious. Okay? And it's going to be the same for infit, same guidelines for infit and outfit. And then this column, very important, this is the point measure column. Not the corrected item total correlation, but probably overstated by about 0.10. Now, when we first began to analyze the curiosity scale, we found that the first item was negatively correlated. The first time you analyze any scale, the first thing that you will do is go to the item polarity table and look at the direction of the correlations. And if you find that any items are negatively correlated, well, those items don't covary with the construct. Those items are varying inversely with the construct. So that means that you want to go to the data and change the scoring direction of the items. Another table that you're going to look at is called the empirical item categories table. And this is going to essentially give you the difficulty level of each level of the items. Okay? And the items are going to be over here on the right, and they're going to vary from easiest at the bottom to the hardest at the top. And kind of the general slope of this is going to give you an idea of how strongly the item hierarchy is represented in the data. Okay? And then the last thing we talked about was how to find dependent items. In SPSS, we didn't have an easy way to do this. We had to look for items that correlated, say, 0.50 or greater. In WinSteps, we have an easy way of doing this. WinSteps gives us the correlation of the item residuals with the ROS dimension removed. Essentially, you go to the dimensionality output, which is on the diagnosis screen, and you scroll all the way down, and you'll find a list of the most dependent items. That is, the most highly correlated items. And the idea here with dependent items is essentially that items should be alike in that they tap the ROS dimension, and they should be different in every other way. Now, the values that you're looking at are going to be values that are more extreme than 0.30 or minus 0.30. Anything that's more extreme than that is going to be suspicious. But you have to be aware of the fact that right now you're analyzing the IP data, and the data were gathered over the last 10 years, so they were actually gathered over different occasions. Okay? So in this particular example, you find 2 items here: consider myself to be a wise person and am considered to be a wise person. Those 2 items are correlated 0.39. The residual correlation is telling us that those 2 items are too strongly related, and one of those items simply has to go. So what you would do is you would look at all of the other psychometric characteristics. You would look at the targeting, you would look at the fit statistics, you would look at the point measure correlation, and you would determine which item has the most strikes against it, and that item would be removed. Okay? So let's continue now with this same idea, and we're going to talk a little more generally about how to evaluate dimensionality. When you selected dimensionality from the diagnosis screen, you probably wondered what was above the dependent items. And the stuff above the dependent items is really all intended to assess what's called unidimensionality, which is a word that we've heard a lot before. And unidimensionality is really related to the scientific method, strongly related to the scientific method. Because what we try to do in science, well, we try to make one change and see what happens. So we've got one group, we want to make one change to that group, and then we want to observe that. We want to observe both groups very closely. And if something happens as a result of making that one change, then assuming we have scientific control and there's no confounds, we can measure the effect and infer causality. In terms of measurement, we want to do the same thing. We want to measure one and only one thing. If the scale measures two things, then measurement is confounded, right? So imagine that you go to National Bookstore and you buy a ruler and you're going to put some carpet down in your living room. You bring the ruler home. It's a really cold night. You bundle up tight. You wake up in the morning. It's still a cold morning. You look at the ruler and the ruler is half the size that it was before. The cold weather has caused your ruler to contract. That would be a problem, right? Or it's a really warm day and the warmth has caused the ruler to expand. And now you've got the idea that the ruler is no longer measuring one thing. That maybe the ruler is better as a thermometer than it is as a ruler, right? Because the ruler is beginning to expand. So if a ruler measured more than one thing, it would be pretty useless as a ruler. So we simply want the ruler to measure one and only one thing. And we know that ideally, all of the items on our scale are going to be composed of signal and noise, okay? And that ideally, all of the error variances of the items are going to be randomly distributed. And when the error variances of the items are randomly distributed, then the signal is going to accumulate in the middle. And this is going to be the ideal case. And this is going to be the case that the Roche analysis is basically going to aim for. The problem with this is that it's too ideal. And in real life, the error variances of the items are rarely randomly distributed. And that's why, for example, if you take the items and you feed them into a factor analysis, you often get more than one factor out of the factor analysis. So if you look at the way these item variances are arranged, each circle is one item, and you can see here that there's basically three dimensions here. There's two subdimensions. There's a strong factor over here, and there's a somewhat weaker factor over here, and yet the items do overlap and the signal is accumulating in the middle. So the items here have got three reasons to aggregate. Okay, there's three factors that are basically represented, three dimensions that are basically represented in the data. So ideally, the Roche dimension, our measurement dimension, would be the dimension that's most strongly represented in the data. And when that happens, well, the aggregation is going to occur and the signal is going to add up most strongly on the Roche dimension. But if you look at this, let's look at this simple case. We have the Roche dimension here, and we have two item residuals here that are strongly correlated. Well, what does it mean for items to be correlated? Basically, it means that what happens to one item tends to happen to the other item, right? So if one of these correlated items is endorsed, then the other item tends to be endorsed. And that begins to affect measurement. Because now what happens is that there's no longer one dimension in the data. As soon as we have two item residuals that are strongly related, now there's a second dimension that's present in the data. Because what happens to one of these items tends to happen to the other item. Okay? So now we have what's called a competing dimension in the data. And we can think of this idea, earlier in the semester we looked for clones. We looked for highly correlated items or near clones. We looked for dependent items. All of this stuff essentially forms a continuum. So the most extreme example, let's say that your secretary accidentally duplicates an item. This is obviously a dependent item. Number 11 is the same as number 15, or number 100 is the same as number 102. That would not be a good situation. Basically, the test would have to be reprinted because you can see that this is obviously a dependent item. You have near clones. You have items that are too closely phrased. They're too similar. You have dependent items in which the phrasing of one item depends upon another item in some way. And then you have the situation of local independence, which is what we want, in which each item is essentially the item residuals. They don't correlate at all. Okay, the correlation between the item residuals is 0. In essence, we can say that the Roche dimension is the only dimension in the data. And this is different than what we're used to with classical test theory and factor analysis. In classical test theory and factor analysis, we were very happy to find subdimensions. Okay? If we found subdimensions, if we found that our items factored into 3 subdimensions, 3 parts of the construct, we could look at those subdimensions and we could compare them to the construct definition, and we hoped for convergence between those 2 things. In the Roche model, we're going to take another attitude. Since we want the Roche dimension to be the strongest dimension in the data, we're going to try to kill the competing dimensions. Okay, so this is your chance to get aggressive in psychometrics, and it's okay. Okay, so remember, the theory is going to dictate the item hierarchy. We want the item hierarchy to be the only thing that exists in the data. How can we systematically assess whether the item hierarchy, whether the theory is the only thing that's going to be measured by the items? And the answer to this question is that we do a principal components analysis of the item residuals with the Roche dimension removed. All right. I'll say it again. We do a principal components analysis of the item residuals with the Roche dimension removed, with no rotation. Okay? So this down here, this is the same thing that you saw before, this stuff down here, and now the Roche dimension has been removed from that. So essentially all of the signal represented by the Roche dimension has been removed from the data, and we're going to do a principal components analysis of what's left. And if the item residuals are randomly distributed the way we want them to be, this means that there's not going to be anything left. Our principal components analysis will find nothing. There will be nothing there to find. Because remember, the purpose of a factor analysis or a principal components analysis is to find out what things go together. So a principal components analysis, a factor analysis, looks for latent dimensions in the data. In this situation, we're factor analyzing the item residuals with the Roche dimension removed. We're factor analyzing what should be noise. And if it really is noise, then there's going to be nothing. We're not going to find anything there. But if there's signal in the data, then the principal components analysis is going to find that. Okay? So now I want you guys to go ahead and start WinSteps. And go ahead and analyze the lovelearncuriosity.txt file. So were you guys able to analyze the file? Who's analyzed the file? There should be a file called lovelearncuriosity.txt that I sent. So just start WinSteps and analyze that file. Well, you can just start the file first, and then I want you to go to the edit menu. You guys can go ahead and go to the edit menu and open the command file. Okay, so we're all together and you guys have got the command file open, right? Okay, so once you open the command file, go ahead and scroll down and look for the iSelect statement. And you're going to see where it says iSelect equals L. And let me tell you what I did with this. This is the VIA data, the IP VIA data that you're used to, except I thought I would put love of learning and curiosity together in the same scale. So I changed the names of the scales to something that where I could select both sets of items at the same time. So I changed curiosity to LCR, I renamed curiosity to LCR, and I renamed love of learning to LVL. Okay? And then there was also a scale called capacity for love, which was just love, but I put a C in front of it so that it wouldn't get selected, so the items of that wouldn't get selected. So that meant that all I had to do is have iSelect equals L, and that would select the items from both scales into a single analysis. Because as we've talked about previously, we have our doubts as to whether these are separate scales, right? I don't know whether these are separate scales or are the same scale. Are they measuring the same thing? I don't know. When we calculated the raw scores earlier and looked at a correlation matrix, we found that the scales were correlated 0.60. Well, 0.60, a 0.60 correlation between scales is as high as a good item scale correlation, right? So there's the possibility that these scales may be the same scale. So essentially what I did here is I just set things up so that I could select and analyze the items together as if they were the same scale, and we'll see what happens. All right? So the first thing that I do, I go to the diagnosis menu and look at the dimensionality output. Okay, so go ahead and do that. So that should pop up the results of the dimensionality analysis in Notepad, right? So it's diagnosis menu dimensionality. So we're all together? Okay. So what you're going to see here is a table of standardized residual variance. It says in eigenvalue units. One eigenvalue is equal to the variance of one variable, one item. And you're going to see there's a couple of entries here. Raw variance explained by the measures and then another one that says raw unexplained variance, okay, the total unexplained variance. And that's going to be the two principal sources of variance in the data. Those are both broken down further, but those are the two main categories of variance in the data, and those two are going to add to 100%. So in the items as we have them, we haven't done any item selection yet, and in the items as we have them, we've got, looks like raw variance explained by the measures is 39.3%, and the raw variance explained, the raw unexplained variance is 60.7%. Okay, and those two numbers are going to add to 100%. And then if we look at the raw variance explained by the measures, that's broken up into the raw variance explained by the persons and the raw variance explained by the items. Okay, so the 39.3% is broken down further into variance explained by persons and variance explained by items, and that's pretty cool, right? You can't possibly imagine SPSS ever coming up with anything like this. So to be able to break the variance down into that explained by the persons and items, that's pretty nice. And then underneath that, you're going to notice that there is raw unexplained variance, and you can see that the raw unexplained variance is 60.7%. And then I've got a little red box drawn around some numbers here, and you'll see that it says unexplained variance in first contrast, unexplained variance in second contrast, unexplained variance in third contrast, and so forth, all the way up to the fifth contrast. Well, remember, this is the result of a principal components analysis of the item residuals with the Roche dimension removed. So these are the competing dimensions right here, okay? And the reason they're called contrasts goes all the way back to this slide, because you can see here that I've got the Roche dimension removed. So when I look at the results of this principal components analysis, I'm essentially contrasting the stuff that's over here with the stuff that's over here. The Roche dimension is gone. Ideally, all of the signal is gone from the residual variance. Okay, the residual variance is just noise. There's no signal left in it. So ideally, all of that would be gone. And these numbers here, unexplained variance in the first contrast, this is 2.4 eigenvalue units. What this is saying is that the first contrast has a value of 2.4 items. That's how strong it is. Okay, it's as if the strongest competing dimension to the Roche dimension contained 2.4 items. Okay, and that's going to make up 5.1% of the variance. All right, and then the next one is 2.1, and the next one is 2.0. So this is how strong this 2.1, these eigenvalue units, this is how strong these competing dimensions are. As you can see, the first dimension is 2.4, the second is 2.1, the next one is 2.0. Essentially, the dimensions become less interesting as we go down the line. Typically, the only ones that we're going to look at, often the only one that we'll look at will be the first contrast. That will often be the only one that we'll look at. If we have a scale that consists of many items, we might look at the first, second, and third contrast. It's going to be rare to look at the fourth and the fifth contrast. It's nice to see them there because you see them there and you know where the noise is. Things tend to drop off pretty fast. So typically you're going to be looking at the amount of variance in the first and the second contrast. Sometimes what will happen is that you drop an item and these two will change places, because every time you do an item selection, the amount of variance in the first and second contrast will change. But it's typically those two that you're going to look at. And you have to essentially determine how significant they are. So you remember that when we did factor analysis, anytime you do factor analysis, you're going to extract a lot of different factors. Usually only the first, second, or the third factors are going to be interpreted, maybe the fourth and fifth sometimes if you're dealing with lexical terms, right? But typically it's the first several factors that are going to constitute the lion's share of the variance. And then Cattell said that everything else was scree or rubble or noise factors. Okay? So the question is, at what threshold do these competing dimensions become significant? When do you have to address them? And the general rule of thumb here is 2 points determine a line, so 2 items determine a dimension, and anything that is 2 eigenvalue units or less, the rule of thumb, these are essentially noise. So if you look at the first contrast and you find that the first contrast is 1.9 eigenvalue units, you would pretty much be within your rights to say, okay, this is okay, I don't have to worry about this. You might scroll down the output and see what's there. It would probably be a good idea to scroll down the output and see what's there, but it's less than 2, so most people are going to say that's noise. And you want to try to find an idea, you want to get an idea of how strong the Roche dimension is to the strongest competing dimension. So if you look back at the table, you find that the raw variance explained by the items, that's the strength of the Roche dimension, right? The raw variance explained by the items, it's the item hierarchy that we're interested in, so that has a strength of 25.2% of the variance here. And the first contrast is explaining 5.1% of the total variance. So if we divide 25.2 by 5.1, it means that the Roche dimension is about 5 times more powerful than the nearest competing dimension. And that's pretty good, okay? Another way to look at this, which would be totally defensible, would be to say, well, we expect the noise to have 2 eigenvalue units anyway, so it wouldn't be 5.1 because that's actually a percentage, but we could say 2.4 minus 2, we could say that the first contrast actually has 0.4 eigenvalue units of signal, and that's going to make our Roche dimension appear to be much more significant, right? Because two of those eigenvalue units are supposed to be simply noise. Okay. Now go ahead and scroll down the output. You're looking at the residual table. Go ahead and scroll down the output, and you pass a graph. Keep going, and you'll come to this place where you have 2 large columns of items side by side. So you're going to have here, it says contrast 1, and then it's going to have the loadings, and it's going to have another set of items that's over here on the right. Do you guys see that? If you're on a netbook and your screen is kind of narrow, you might miss the second column of items over here. So are we all together? Okay. So you can either choose to look at this table or you can look at the one below it. And if you scroll down just a little bit further, you'll find the one below it, which is really the same. It's the same items, but they're printed vertically instead of horizontally. And I guess Mike did that because some screens are narrower and some screens are wider. So you can look at either one of these, and they're going to be the same. So if we look at the item loadings on the first contrast, remember we're calling them contrast because it's a contrast between what's left in the data. The signal is supposed to already be taken out of the data through the Roche dimension has been removed. Okay. So if we look at the first contrast, we look at the loadings on the first contrast, and we find it's these items. Read all the time, read a large variety of books, and I think the item is don't read nonfiction for fun. And those 3 items are correlated 0.62, or they load 0.62, 0.55, and 0.40.
with the first contrast. Okay, and really, what is this saying to us? Well, what it's saying to us is that perhaps reading is evidence of curiosity, but it might not measure curiosity as strongly as some of the other items do. That's a possibility. Another possibility is that there's just this pocket of reading items in the scale, and maybe that pocket of reading items shouldn't be there, because we've got 3 items that seem to be pretty closely related. So let's check this out. Go ahead and scroll all the way down to the bottom. Remember where you are, and scroll all the way down to the bottom of the dimensionality output. Okay, so when you get to the bottom of the dimensionality output, you can see the dependent items, and you can see that there's a couple of sets of dependent items that are in excess of 0.30, and the first one, the biggest one, the one that we really have to worry about, is read a large variety of books and read all the time. So these items are so strongly related that, yeah, they're showing up on our list of dependent items, and because we haven't removed them yet, they're also showing up in the first contrast. Okay? And then the second set of dependent items are these: I'm never bored and I'm always busy with something interesting, and the item residuals there are correlated 0.31. So if you scroll down to contrast 3, or actually you'll have to scroll up to contrast 3 since you're on the dependent items, and that's at the bottom. So scroll up to contrast 3, and you're going to find that these 2 items basically define contrast 3. I'm always busy with something and am never bored. Okay? So the lesson here is that when you're considering dimensionality, the first thing that you have to deal with, just like you have to deal with it pretty much the first thing in any analysis, you want to delete the redundant items first. And if you don't delete the redundant items first, then the redundant items are going to show up probably in terms of defining the first contrast, the second contrast, or the third contrast. So you'll see them eventually, because essentially they define a dimension. The question is here, once you define a dimension, how are you going to interpret it? Okay? And you'll notice that there is a column here. Scroll all the way back up to contrast 1. And again, ordinarily we would have already handled this because we would have already removed some of the reading items because they're dependent items. But if you scroll back to contrast 1, you'll see that there's this central column here of letters. You'll see this entry number column pretty much in the center. And then you see these capital letters: A, B, C, D, E, F, G, H. And then below that, these are the items with the positive loadings. And then below that, the items with the negative loadings have A, B, C, D, E, F, G, and so on. Okay? So every item has either a capital letter or a small letter. And these are called contrasts, remember. So we want to try to get an idea where the extra dimension emerges in the data. So if you look at the graph which is above the list of items, okay, you'll see this. And the vertical axis on this graph is going to be the contrast loading, and the horizontal axis is going to be the item measure or item difficulty. And essentially what you're doing, you're looking for where A, B, and C are, big A, B, and C, and little a and B, and you want to see where those are at. Okay? And this is going to tell you, these could be easily placed, they could be placed anywhere. You can see here that this is not a scatter plot, so this dimension is picking up some kind of signal. What's that, AJ? Okay. Okay. All right. So you want to find a way to interpret these contrasts. You want to find a way to determine what each contrast means, and you can see here that you have a list of items, and the items have A, B, C, and D, capital letters for the positively loaded items, small letters for the negatively loaded items. If you look at the graph, you can find capital A, B, and C up here, and this will tell you where the dimension emerges in the data. All right? So maybe you have a situation in which the dimension tends to emerge only at the upper end. Okay? It tends to emerge at high levels of difficulty. You guys still hear me? Okay, just checking. So you want to try to compare the thing that you're doing. You're not just looking at the item loadings. You're actually comparing the content of the most highly loaded items up here, the most highly loaded positively items, to the strongest negatively loaded items. And you're looking for a contrast between those two. So the most high positively loaded items are read all the time, read a large variety of books, don't read nonfiction books for fun. The strongest loaded negative items are look forward to the opportunity to learn and grow, love to learn new things. So maybe the contrast is that the first is a very specific method of curiosity, of satisfying curiosity, and the second is an attitude. So that might be the contrast. That might be one interpretation of that contrast. So which item are you going to delete? Well, as I said earlier, ideally we would have already handled this situation because we would have deleted the dependent items, but we would handle the high residual correlations between items first. We would handle the most poorly fitting items second, handle narrow and disordered items third, and then last you would probably handle dimensionality. And when you do handle dimensionality, you'll notice that there are three columns here. One is infit, one is outfit, and one is measure. So Mike Lineker has done us a service of putting infit and outfit right next to the loadings, and many times what you'll see is that the item that tends to define a contrast, that item doesn't fit. And many times that makes your decision about which item you're going to delete. So you don't have to look at anything else. You can simply look at the infit and the outfit. You can see that it's extreme, and then that item's going to have to go. Okay? In other cases, it's not so clear. The fit of the items may be okay, and you have to look at the empirical item categories and let that make your decision. All right? Yes. Which one? I would delete one item at a time because everything is going to change as a result of deleting that item. Particularly if you have a small number of items, that could produce a big change in the scale. So I would delete one item at a time. If you have a large number of items, say you're dealing with 30 items, and say the fit statistics on the items are obviously bad, say in excess of 1.7 or 2.0, then I think it would be okay to delete a couple of items at a time. But if it's a short scale, I would definitely delete one item at a time. Right. Yeah. Well, what's going to happen here is that this item is going to get deleted based on its fit statistics alone. So this item has got to go. C has got to go based on its fit statistics alone. The 2.0 outfit is egregious, and that item is not going to make it. So that item is simply not going to make it. It's going to be thrown out. At that point, you could decide to recalculate the dimensionality, and you can see what happens as a result of that. Maybe the amount of variance which is in this contrast is down to 1.9, and you don't have to do anything about it. But as we know, these reading items are still very highly correlated, so one of these reading items has got to go as well. So C is going to get deleted based on its fit statistics. Either A or B is going to get deleted because those are dependent items. And then you have to see what happens. Any other questions? Okay, so just sticking with the idea of what do we do about it, we have here this interesting quote from Mike Lineker, and he says, "What do we do about these extra dimensions? Often our decision is nothing." On a math test, we will get a big contrast between algebra and word problems. We know that they are conceptually different, but they are both part of math. We don't want to omit either of them, and we don't want to separate algebra measures and word problem measures. Okay, so let's say that you're measuring arithmetic, and you've got these 5 item types, and it's addition, subtraction, multiplication, division, and word problems. And then you look at the contrast and you find, uh-oh, my word problems and my multiplication problems tend to define a contrast. What are you going to do about that? And according to Mike, the answer may well be nothing. You just want to make sure that the various parts of the instrument are balanced. Okay? So the situation would be something like this. Maybe you find that your addition items soak up a lot of the variance in the first contrast. So maybe you want to delete a couple of items from your addition and just make sure everything is balanced. But when you look at all of the contrast, what you find is that addition tends to define the first contrast, subtraction defines the second contrast, multiplication the third, division the fourth. And the reason for that is there are only 4 or 5 different arithmetic items anyway, 4 basic item types, and then 5 if you include word problems. So in that situation, you have a situation in which your items form a natural grouping, and there's probably not a whole lot to do about it. The situation that we just dealt with was a situation where we have an excessive number of reading items. Okay, we had 2 reading items that we found as dependent items, but we have 3 reading items for whatever reason. For whatever reason, Peterson and Seligman decided to put 3 reading items into the love of learning scale, and those items are highly correlated, and those items form a competing dimension. And since these items are so highly correlated and they do form a competing dimension, well, when the signal aggregates, whenever somebody endorses an item, and you look at the scale total. The scale total is no longer about the Roche dimension. The scale total also represents some aggregation of signal that is taking place over these 3 items. This dimension is competing with the Roche dimension. If somebody endorses the item read all the time, they tend to endorse the item read a large variety of books. It's very difficult to read all the time without reading a variety of books, right? Okay. If they endorse one of these 2 items, they also tend to endorse this item, don't read nonfiction books for fun. So all of these items are correlated. You endorse one of them, you intend to endorse all of them. The total scale score no longer reflects the Roche dimension. It reflects signal that aggregates over these 3 items. And that means in a Roche context, we want only the signal, we want only the dimension that reflects the item hierarchy to be represented in the total score. So we're going to kill the extra dimensions. We're going to get rid of them. We're going to assassinate them. And the dimensionality results allow us to do that and to do it rigorously. And we do that so that the item hierarchy is the only thing that remains present in the items. Okay? So what I will typically do is I'll look at the items that are in the first contrast and second contrast. Anything that's greater than 2.0, I'll look at the items that are loaded, say, beyond 0.40, because those are really the only ones that are significantly loaded anyway. And I'm going to find the item with the most strikes against it. Many times you'll see that an item which is loaded high on a contrast, it tends to assess some other dimension, and as a result of that, the fit statistics are not really good. So that will often make your decision. If the fit statistics don't make your decision, then you're going to have to find the item with the most strikes against it. Look for an item that's poorly targeted, or look for an item that's narrow or disordered. Look for an item that's inconsistent with the theory of the construct. You have to find some rationale by which you can justify throwing out one of the items. Okay? So as I said earlier, the fit statistics are right here. In this case, am never bored has a very poor fit, 1.5, 1.58. Go ahead and scroll down to the third contrast so that you can see this for yourself. So you guys found the third contrast? Yes? Okay, so you scroll down to the third contrast and you see that, well, the item here, am always busy with something, that's loaded 0.56. The item am never bored, that's loaded 0.51. These happen to be dependent items. We found them in the list, but pretend that they're not for a moment. Well, this is a situation that you might encounter. You've got two items, their loading is pretty close, 0.56 is pretty close to 0.51. Which item are you going to delete? Well, it's a pretty easy decision, because if you look at the fit here, the item am never bored has a poor fit. The outfit is 1.58. The other item has a fairly decent fit, so the item am never bored, even though it loads slightly less, the fit is really bad. That item is going to go, right? And once that item is removed, the amount of variance that's in the contrast is going to decrease. That may well pull the number below 2.0, and you don't have to worry about it anymore. Or it may pull it down to 2.1, but the Roche dimension is so powerful, 2.1 is not much greater than 2, right? 2.5 is not much greater than 2. So if the Roche dimension is really powerful, you might just, you might decide not to worry about it at all. You might just delete the poorly fitting item. Maybe this pulls the amount of variance in the contrast down to 2.5, and you say, I'm just going to let it go. The competing dimension isn't that powerful anyway. Okay? So this will become an additional way that you guys can use to select items. In addition to everything else, in addition to the point measure correlation, in addition to the fit, in addition to the empirical item categories, now you have something else to look at. Now you can look at the extent that there are multiple dimensions in the data, and it's kind of like whack-a-mole. The idea here is that you continue thumping the competing dimensions until they're no longer present. The Roche dimension is the only dimension in the data. Now, there are ways to do item selection procedures in order to try to maximize your item hierarchy. So earlier, I'll just scroll back up here, and we had the raw variance that's explained by the items. The more variance that's explained by the items, the stronger the item hierarchy is present in the data. That makes sense, right? So if we want to try to maximize that number, we do have a way to do it. So I'll just show you some analysis that I did. Let me give you a little background on it. This is one of the scales that we put together for DSM-5. The APA, the American Psychiatric Association, was entertaining radical changes in personality pathology for DSM-5. They were talking about pathology of identity as one of the fundamental criteria for personality pathology. And according to APA, pathology of identity had three parts associated with it: problems with boundaries, failure to respect boundaries, problems with self-esteem regulation, and problems with emotion regulation.
So if you have problems with identity, you don't know where your identity ends and other people's begins, you may not be able to keep secrets. Your self-esteem, in a healthy situation, your self-esteem needs to be positive rather than negative, and your self-esteem needs to be stable. So the narcissistic personality, for example, would be an example of someone who does not have a stable self-esteem. If a narcissist comes under threat, well, they may inflate their self-esteem in order to defend themselves against the threat. And then finally, emotion regulation. And you see this most strongly represented in the borderline. So whenever anyone thinks of problems with emotion regulation, they automatically think of borderline. And the borderline is the most famous personality disorder for having problems with identity. But the fact of the matter is that if you systematically assess these people, you find that most of the personality disorders, if not all of them, have problems with identity formation. And Otto Kernberg calls this levels of personality organization. Okay, identity is very poorly formed in most of the personality disorders. And that tends to leave the personality disorders, personality pathology, that tends to leave this entire area, and it's been very contentious and will continue to be. This entire area seems to be, it seems to exist at the cusp of two major models. One is the personality trait model, and the other is the medical model. If you have a situation where someone has, for lack of a better term, good ego strength, they're well organized, they exist at a higher level of personality organization, all of those are psychoanalytic terms, it seems as if a trait model might be most appropriate. On the other hand, if you have somebody that has poor emotion regulation, their mood is highly variable and erratic, they're set off by seemingly innocent comments, this person can seem to be symptomatic. And the psychoanalysts say that there's an entire continuum here in the terms of the way that the self-construct or identity is organized and regulated. At the higher levels, a trait model would be more appropriate. At the lower levels, a medical model would be more appropriate. You need items to assess this entire dimension. So if DSM-5 was going to move over to a trait model, the question is, since there is no ego in the trait model, right? That the whole idea of the ego, the integrating faculty of the mind, that doesn't exist in a trait model. How would you then assess this level of personality organization? So we came up with items to try to do this, and these were administered to undergrads. And there were items in here like feel hollow, like there's nothing inside me. So this is a typical complaint of many borderlines and narcissists. Or problems with self-esteem regulation, go through so many changes in the way I experience myself. Feel too confused to have a consistent set of moral standards. A lack of authenticity, feel more like an actor than a real person. Have problems describing who I am. Obviously, if you have somebody who has poorly formed identity, they don't know who they are. You ask them to reflect on it, and they're going to have difficulty telling you what kind of person they are. If I ask you what kind of person you are, you'll be able to tell me with some precision because you have a personal history and experiences that you can reflect on. Many patients with personality pathology do not. Think I know myself one moment and feel completely lost the next. Fluctuations of identity. Harm friendships because I can't keep a secret. So these are the items that formed our level of personality organization scale. You guys don't have the data, but if you did and you were to scroll down and actually look at the data at the bottom, you would see something like this. You would see this pattern. And what you would see here, this is the actual data here. These are the endorsement. It's on a 4-point scale, and you would see a lot of dots here. And as you know, the dots represent essentially missing data. And you can see that there's a lot of missing data here. And the reason that there's a lot of missing data is because not all of these items were thought of at the same time. And in fact, the items were actually thought of on different rounds. And because missing data doesn't hurt us in the Roche model, what we're able to do is in round A of data collection, we think of a set of items, think of 10 items, think of 15 items. You collect data on those in round A, and then in round B, it suddenly occurs to you, wait a minute, I've thought of some more good items. And then you simply add those good items to the list.
but you don't have to collect data on all of your Form A items. You can decide to collect data on a subset of your Form A items. So the items A and items B Form A and Form B overlap, Form C and Form D overlap. Each form overlaps in terms of a number of items, and that allows you to basically, eventually through a Roche analysis, because missing data doesn't hurt us, the item lists all overlap. We're able to analyze all of those items together as a scale, so we don't have to go out and gather complete data every single round of data collection. And that makes things actually a little bit easier and a little bit more interesting. Okay? So the item here that I immediately deleted because it didn't seem to be on the scale to me, this was item 20. I've actually forgotten what the item text of that was, but you can see here that it's a narrow item, 4321. It's the most narrow item of the lot. So when I look at the empirical item categories, the fit is a problem. The fit was high. The fit was like above 0.5. And then I look at the empirical item categories, and they're narrow, and that's telling me that the item is not on the scale. Okay? So after I delete item 20, then I'm left with this situation. Okay? So what you're looking at here is a lot of items that vary strongly with the trait, and there's a little bit of a slope here. But I'm trying to select the items in such a way that I maximize the presence of the item hierarchy, that I maximize the amount of variance that's accounted for by the items. Okay? And when I start out, my baseline these are my baseline values. I've got 1.7 eigenvalue units of variance in the first contrast, so I'm not really worried about that. The raw variance explained by the items is 15.6%, okay, versus 5% down here. This is telling me that most of the items are basically on construct. When I look at the empirical item categories and I see that they're spread out this way, you guys still there? Okay. AJ's cam disappeared. I can't see you guys anymore, so thought maybe I'd lost you. So when I look at the empirical item categories and I see they're spread out like this, and I see that I don't really have any variance being significantly accounted for in the first contrast, this is telling me that all of my items are basically on construct. Okay? I look at the correlated item residuals, and they're okay. The biggest value is minus 0.20. All right, so I don't really have much to worry about here. And I would like to choose my items so that I get more of a slope. And how am I going to do this? And as it turns out, doing this is actually fairly easy. So I'm going to look at this list of the empirical item categories, and I'm just going to try to choose the items. I'm just going to try to choose items that, I'm going to pick out the items that interfere with the slope. So you can see this item, field pressure to take on any identity the group demands. This item is narrow compared to the others, so that item is going to go. This item, confuse my own wants and needs with those of others. That item is narrow compared to the others. It's going to go. Item 18, find that most people feel a sense of emptiness. That item doesn't contribute to this slope to the right. That item is going to go. And then this item 10, sometimes like myself, sometimes hate myself. This item isn't contributing to that slope. It's going to go. And once I delete those items, that's going to leave me with this. Okay, so I delete 1, 13, 18, and 10. And I'm left with this. And now you can see what's happened. The levels of the remaining item have been spread apart a little bit. It's as if each item serves as a constraint on the others, so that if you have too many items in the scale, the levels are close together. But now I've deleted some items, I've deleted the narrow items, and the remaining items have somewhat spread apart. And you can see that I have a little bit more of a slope to the right. And again, I'm just going to find items here that are narrow or items that look like they don't contribute to the slope, and I'm going to delete them.
So I'm going to delete 9, 11, and 17 this round. And once I do that, I'm left with this. And this item, feel too confused to have a consistent moral standard. This item is definitely narrow compared to the others. So I'm going to decide to delete 7, 8, and 16. That's going to leave me with this. And then I decide to delete item 15. And finally, I'm left with this. And as you can see, now I definitely have a slope to the right. Okay? So yeah. And I'm also tempted to delete item 19 because you'll notice that the 3 and the 4 are so close together. Had to look at that for a minute. So I'm tempted to delete this item, but I know from previous experience that when this happens, and this is a difficult item, remember this is the items at the top are the most difficult items. Well, what tends to happen is that the 3 and the 4 may have very few people in it. So when I look at the number of people that are actually at this level, there's only 8 people and almost 1,000 that endorse the item at level 4. Okay, so that item I'm going to go ahead and leave. And let's see. So the results are, after I do this item selection, I now have 54% of the variance is explained. Total variance is explained. When I started, I had 44.9, so I've raised the amount of variance explained by almost 10%. And now 22.3% is explained by the items versus 15.6% of the variance at the beginning. So you might actually find another pathway through the items that results in even more variance explained by the items. I played around with it a little bit. I actually found that I could get it up to 35%. If I chose the items the right way, I could get it up to 35% of the variance that was explained by the items. Unfortunately, if you delete item 19, what happens? Well, if you delete item 19, it looks like a bad item because the 3 and the 4 are close together. If that fooled you, if you didn't realize that there are just very few people at level 4 here, and you decided to delete this item, the amount of variance explained drops back to 52.5 total and 15.6 variance explained by the items. So you really lose a lot of variance explained by the items if you delete your most difficult item. So the take-home lesson from this is that demonstrating an item hierarchy is going to require items that are both very easy and very hard. And if you delete the easiest item or the hardest item, that's going to narrow the range of item difficulties, and that's going to attenuate your item hierarchy. Okay? And then the question for you as you go through this process of trying to maximize the item hierarchy, if you decide to do that, do the resulting items converge with your theory? Because in personality scales, we really haven't tried to set forward a theory that could dictate the items. Do you find a theory there in the resulting items, or don't you? All right. And this has got some interesting implications for our project because, as you remember, we tried to create items of enormous difficulty. The problem with virtues items is that all of the virtues items are too easy. It's as if the subjects are sitting there going down a list of items and saying, "Oh, that's a very virtuous item. That's me. That's me. That's me. That's me." So they're saying agree or strongly agree to all of the items. That makes the virtues items tend to be very easy. We tried to invent items that would be very hard. So we should have items that span an enormous range of difficulty. We'll have to see what happens. We'll have to see what happens with the data. You guys still there? Okay, because I can't see you now. AJ, can you turn the cam on? Oh, you can't see me either. But you can still see my PowerPoint, right? Okay. Yeah, go ahead and take a break. Question?
You have to approach the mic. I can't hear you well. Hi. You're talking about the empirical item categories table. Yeah, the empirical item categories table is absolutely something that you should use as a criterion for deleting items. That's one of the most useful. That's one of the most useful things to look at in terms of deleting items. And if you have an item that has a high outfit, say 1.5, 1.6, something like that, that item either has a lot of noise in it or it's not on the scale. That item is going to tend to be narrow or disordered anyway on the empirical item categories table. So you're going to see the problem with that item reflected usually in both places. So absolutely it's okay to look at the empirical item categories table. You should be looking at that. And you should be deleting items that are narrow, because the best items are going to be those items that span the greatest range of the trait, right? If an item is really on construct, then you're going to see the levels of the item spread pretty evenly, and they're going to be in order. If the levels of a Likert type item are close together, well, that item is either a bad item, it's not on the trait, there's something wrong with that item, so yeah, probably delete it. You have to get a feel for it. There's kind of a rhythm that you can get into when you're looking at items and you're analyzing items in your head and you're beginning to delete them. The first thing that you're always going to look at is the residual item correlations. You'll always look at that first in order to delete clones. You could decide to look at everything next. You could look at dimensionality. You could look at empirical item categories. You could look at infit and outfit, and you could look for a worst offender item. In other words, you look for an item that has bad fit, an item that is narrow in the empirical item categories, an item that contributes to an extra dimension. That item has 3 strikes against it, so that item has probably got to go, right? So you can think of it as like a police lineup. You can think of your items as criminals, and they're all in a police lineup. And you're looking for the worst offender, and the worst offender is the one that gets convicted and has to go. Any other questions? Yeah, go ahead and take a break. Go ahead and take a 10-minute break. AJ, I think I'm going to go ahead and stop here with the lecture so that you guys have a chance to actually do some analysis in class. And just go ahead and guide them as you did last time. Can we switch to Skype? Yeah, because you guys have got like an hour and a half left, right? Yeah, so go ahead and use I still got the score table that I want to discuss, but I can start on that next time.
So go ahead and use the rest of the class as a lab, and then let's switch to Skype so that I want to meet with each one of the students individually. Okay.